Okay, so these kids are going to run to the center, but I'm going to have to backtrack just a little bit and define the principles of angular momentum so that we can make sense of what will happen to the kids as they run really fast in toward the center. And this, by the way, is going to be similar to what an ice skater would do if, say, she pulls in her arms quickly and starts to spin faster. So the idea then is we'll define angular momentum to be equal to I omega. Now, using the same correspondence, if we define linear momentum, P, to be mass times velocity, and we make the substitution that linear momentum goes to angular momentum, and then as before, mass goes to moment of inertia, and velocity goes to omega, we have a correspondence then between linear momentum and angular momentum, which is similar to our correspondence before with the appropriate substitutions between F equals ma and torque equals I alpha. So what we might expect then is that an angular momentum is going to be the angular equivalent to linear momentum. And we know from before that force is equal to the derivative of linear momentum with respect to time. So if this correspondence holds, we might expect that torque would be the derivative of angular momentum with respect to time. So let's check that. If we set the torque equal to the derivative of angular momentum with respect to time, and we hold I constant, in other words, the mass distribution remains constant, then the torque is just I times d omega dt. But we already know that d omega dt is alpha. Alpha is the derivative of momentum and the second derivative of theta. So we see then that the derivative of angular momentum with respect to time is equal to the torque. Okay, so then the question is, if that's true, then what if the external torques are equal to 0? Okay, now what we mean by external torques here are the torques acting from the outside. So in other words, the adult that was pushing on the merry-go-round stops pushing. And so everything is happening internal to the system. So the kids run to the center. But there's no external torque. Torque external equals 0. So if that's true, and that's equal to dl dt, then that tells us that L equals a constant. Or this defines conservation of angular momentum. If the angular momentum stays constant, then that means that I initial omega initial will equal I final times omega final, because the angular momentum will not change. In just the same way as linear momentum did not change if the external forces were equal to 0. So we see that we have a correspondence here by making these appropriate substitutions that works if we go from force and linear momentum to torque and angular momentum. We have conservation of angular momentum. This means that angular momentum is not created or destroyed, it just changes form. So what did we have beforehand here? Well, we had a bigger I and a smaller omega. So after all the kids run to the center, then we'll still have the moment of inertia of the rotating cylinder, but the moment of inertia of the kids will approach 0 as the kids become arbitrarily close to the center. Okay, and so I final then for this system, once the kids have run to the center, is equal to 4 times the moment of inertia of the kids, which is mr squared, but here we'll put in 0 for the radius of each kid. Now, the kids can't get right on the center, and they can't be right on top of each other, but it's going to be a small value of r, and then we're squaring it. And so to a good approximation, we can set the moment of inertia of the kids equal to 0 when they're all close to the center. Then we'll add to that the moment of inertia of the cylinder, which is the same as before. Okay, so what we have here then is approximately 0 plus 1/2 m, which is the mass of the cylinder, which was, what do we have here, 100 kilograms times 25 meters squared per second, meters squared. 5 squared is 25, so that'd be meters squared. And so this then gives us just 1250 kilogram meters squared for I final. I initial, that's the moment of inertia before the kids run to the center, is then going to be quite a bit larger. That's 6250 kilogram meters squared. And so if we divide one by the other, 6250 divided by 1250, we get 5. I guess I probably could have seen that if I was good with dividing. Okay, and so if the final moment of inertia has dropped by a factor of 5, that tells us that the final omega is going to have increased by a factor of 5. So that means that this thing is going to be rotating 5 times faster than it was before. Okay, and so if we solve this for omega final, this will be equal to I initial divided by I final times omega naught. That's going to be 5 times omega naught. And omega naught we had before as 0.4. So that's going to be 5 times 0.4 radians per second, which will be equal to 2 radians per second. So instead of going at, what was it before, just a few tens of degrees of angle per second, it's going 5 times faster than that. So the kids then start to get dizzy and they go flying off, and they had a great time. Okay, and so that then is a way to keep the total angular momentum constant while changing the mass distribution in such a way as to cause the spin rate to go up. Now we can see that same thing with a look at the data projector. If we have an ice skater, she pulls in her arms and she starts spinning faster. Okay, and so with a mass distribution that's more spread out, as in part A, the moment of inertia is much larger. But then as she pulls in tight, her spin rate goes up. And so this then is the principle of angular momentum. We could have an athlete pull in the barbells, and then he could be spinning at a certain rate until he pulls them in, and then as the moment of inertia drops, the angular velocity goes up, the spin rate goes up. Someone who's diving can control the rate of spin by how extended the body is at any given time. And so an Olympic diver then could spin very rapidly at first by pulling his body in, and then seeing when to open the body up so that you get that perfect 10 trajectory for the Olympics, whenever the Olympics will be held, when that diver enters the water.